Hello, my name is Kaima from Ohio State University. Today I'm going to talk about power control, power constraint performance optimization in computer systems. I believe everybody here has a cell phone, and we may use MP3 players or biosensors in our daily life. Those devices, they look quite different. However, there is one thing in common for all of them. They all use batteries. When the battery is gone, then everything stops. So we really want to extend the battery lifetime of those devices. There is an interesting law for the batteries that we can use to increase the lifetime of the battery. It's called Pucher's law. The law states when we discharge the battery with an irregular power profile, then the battery will be drained out very quickly. However, if we can control the discharge of the battery, never go higher than certain value, then the lifetime of the battery will be extended. Even in both cases, we use the same amount of energy. Unfortunately, in modern computer systems, usually we have an irregular power profile due to the workloads. Different workloads, they stress the device differently. Even for the same workload, at different code segments, the workload, it stresses the device differently. Therefore, there is an incentive for us to control the power consumption of the system, never go higher than certain value in order to extend the battery lifetime. In addition to extend the battery lifetime, power control can also save the design and the implementation cost of a computer system. If we have an irregular power profile for a computer system, we need to design according to the worst case. However, if we can control the power consumption of the system never go higher than certain value, in this case, we can design according to the average case. Since we lower the design target, usually that will buy us design and the implementation cost saving. Another reason to do power control is to ensure thermal safety. We all know that if the temperature of a computer system is too high, the computer chip will burn itself. However, if we look at the temperature, it is the net effect of a power consumption and heat dissipation. So by controlling the power consumption of a computer system, we actually control the root cost of a high temperature. That's how we can ensure the thermal safety of the entire system. Since power control can extend the battery lifetime, it can save design cost. It can also ensure thermal safety. That's why we need to study the power control. And there are a lot of different knobs in order to dynamically change the power consumption of a computer system. Here we introduce dynamic frequency scaling or frequency scaling. In modern computer systems, we can run the processor at a different frequency level. When we run the processor at a high frequency level, then we use more energy, but we have a better performance. In another way, when we run the processor at a low frequency, we use less energy, but we have a degraded performance. So by dynamically changing the frequency of the entire system, we actually can adjust the power consumption of the entire system and explore the power and the performance trade-off. So far, we've learned that a computer system usually have an irregular power profile. And by dynamically changing the frequency of the processor, we can change the power consumption of the system. Our goal is to control the power consumption of the system, never go higher than certain value. And we can design a power controller to do that. We measure the power consumption of the system and compare the power consumption with the power budget. Based on the difference, we can compute the next step of frequency for the computer system to use in order to control the power consumption of the system, never go higher than certain value. This solution looks very straightforward. However, power control problems is very challenging because of the performance consideration. Take the frequency scaling as one example. When we want high performance, we can always set the frequency to the highest value. However, if we keep using the highest frequency level, there is a possibility that the power consumption of the system will violate the power budget. So the problem essentially becomes how we can decide the maximum frequency of a computer system without violating the power budget. Since the power consumption of the system is a dynamic value, it changes from time to time. So how to decide this maximum frequency at runtime is a very challenging problem. On top of that, we also need to consider how to allocate the resources. Also take the frequency scaling as one example. For a multi-core processor, even we come up with a way to decide the total frequency quota of the entire chip. Since different cores can be running at different frequency levels, so how to allocate the overall chip level frequency quota to each core will make a very big difference in terms of performance, because each core is running a different application. So different application needs different frequency. How to assign the frequency to each core will make a very big difference in terms of performance. The reason that power control problems is very challenging is because we need to consider performance. I've been very fortunate to be able to work on this problem, which is to optimize the computer system performance and assign the power budget. Based on this root problem, I conducted several projects. Specifically, they are on component level, chip level, server level, and the system level. On the component level, we look at last level cache system. That we dynamically turn on and turn off a cache way inside one last level cache to maintain the power consumption of the last level cache never go higher than certain value. On the condition of that, we try to optimize the performance of the cache. On the chip level, we look at multi-core or many-core processor. We control the power consumption of the chip and improve the performance of the chip. On the server level, we look at high-performance computing servers. In some of those servers, we have a CPU and a GPU, two computational parts. We discuss how to coordinate those computational units in order to improve the energy efficiency of the entire system. We also discuss how to use power control as an effective knob to optimize the operation cost of a data center. In the following slides, I will introduce two examples. One is on the chip level, it's our ISCA 2011 paper, and the other one is our SuperCap project, which discuss how to use power control to reduce the operation cost of a data center. For the scalable power control for parallel workload on multi-core processor project, we discuss how to assign the frequency of each core in a multi-core processor to control the power consumption of the system never go higher than certain value. On the condition of that, we try to optimize the performance of the entire processor. There has been very nice work before this project. However, we are able to identify that they are either with a slow responsiveness or they assign independent workloads among different cores. However, we all know that one of the fundamental reasons to use multi-core processor is to host a parallel workload. There is a big difference between parallel workload and independent sequential workloads. Here we present an example. For a parallel workload, usually periodically we will have information exchanging points or synchronization points or common barriers. We can name it differently. However, the essential idea is at those points, all the worker threads, they need to exchange information before they can proceed. Here we have an example. If T1 and T2, there are two threads inside one parallel workload. Due to runtime variation, if T1 is running faster than T2, T1 has to wait for T2 at the common barrier until T2 to arrive. By then, they exchange information. After that, they can proceed. In another case, if T2 is running faster than T1, T2 has to wait for T1 at the common barrier until T1 to arrive. By then, they can exchange information. After that, both of them can proceed. The only case there is no waiting here is that T1 and T2, they have a similar progress. We can see it is very different from two independent workloads. If T1 and T2, they are independent, then the execution of T1 will not impact the execution of T2. So we want to leverage the special characteristic of parallel workload in order to improve the overall performance of the system. Our high-level design is consistent with our generic power controller. We also measure the power consumption, compare that with the power budget. Based on the difference, we calculate the frequency of each core. Since we want to resolve two problems, the first one is to improve the responsiveness. The second one is to consider parallel workload. So it is natural for us to break it down into two components. In each component, we address one problem. In the feedback controller, we measure the power consumption of the system and compare that with the power budget. Based on the difference, we calculate the frequency of the entire chip. We also design a partitioner. It will partition the chip level frequency to each core based on the performance of each core. In the feedback controller, we try to improve responsiveness. In the partitioner, we explicitly consider parallel workload. Before we introduce our feedback controller, let's first recap the very simple but very classic heuristic to do power control. Suppose we have a processor, it has multiple frequency levels. If the current power consumption is higher than the power budget, then we decrease the frequency by one step. If after that the power consumption is still higher than the power budget, we further decrease the frequency until the power budget is achieved. We can see this algorithm works very well if we have a limited number of frequency levels. However, what if we have 50 or 100 different frequency levels? In that case, we need 100 steps from the highest frequency value to the lowest frequency value. That's why we say this simple heuristic, the responsiveness is too slow. In order to improve that, we come up with a feedback controller design. Based on the feedback, our controller is designed based on feedback control theory. We also measure the power consumption of the chip as PK and compare PK with the power budget PB. Based on the difference between PK and PB, we calculate the frequency adjustment. The essential idea here is to directly calculate the next step of frequency of the entire chip instead of going through the step-by-step adjustment process. By directly doing the computation, we work around the step-by-step adjustment to improve the responsiveness. After we decide the frequency of the entire system, we need to allocate the frequency of the entire processor to each core. Our high-level idea is shown in this animation. Suppose we have two threads, T1 and T2. Due to runtime variation, T2 is running faster than T1. T2 has to wait for T1 at the common barrier until T1 arrives. During this waiting time, the potential computational cycles and the power are wasted. So we want to avoid that. We want to dynamically identify which thread is running faster and which thread is slow. then we allocate more resource to the slower thread in order to make them have relatively the same progress. So at the common barrier, there will be no waiting here. All the available computational cycles would be used to work on real workload. By doing this, we improve the power efficiency and improve the performance of the entire system. In order to identify the progress of each parallel workload at runtime, we use the thread criticality metric. This metric basically is a weighted cache miss. The higher the criticality metric is, the slower the thread is. That's why we proportionally partition the frequency of the entire chip based on the criticality metric. By doing this, we allocate more frequency to the slower thread to make each thread have relatively the same progress. By doing this, we improve the performance of the entire system. Let's recap our design. We have a feedback controller. It takes the power measurement and the power budget to calculate the frequency of the entire chip. We also have a partitioner. It takes the frequency of the entire chip and the performance of each core to calculate the frequency quota of each core. In the feedback controller, we improve the responsiveness. In the partitioner, we explicitly consider parallel workload. So our entire system achieve our two design objectives. We evaluate our system both on physical testbed and in simulation environment. On our physical testbed, we use an AMD 12-core processor, and we measure the processor power consumption and log the power reading and the performance information in a dedicated server. We hack a CESC simulator to support per-core DVFS and use the simulator to evaluate our system in a larger scale. We also use Parsec and Splash as our workload. In order to validate the effectiveness of our proposed solution, we reproduce two state-of-the-art work to improve the priority and the steepest drop. In the results, we can see that on both physical testbed and in our simulation environment, our proposed scheme can improve the baselines. In this project, we propose frequency partitioning. We explicitly consider parallel workload, and we use power control. We use feedback control as our control theoretical guarantee to control the power consumption of the system, never go higher than certain value, as well as to optimize the performance of the entire system. We evaluate our system both on physical testbed and simulation environment, and our test results show that our proposed solution can improve the baselines. In the previous example, we've shown how to do power control on the chip level. In the next example, I will introduce how to use power control to reduce the operation cost of a data center. It is nice that if we have a frequency scaling to control the power. However, in some servers, there is no frequency scaling support. So what can we do to control the power consumption? One possible solution is to aid an energy storage device and treat the energy storage device and the server as an entire system. Such a system works like this. When the power consumption of the server, the actual power consumption of the server is lower than the power budget, then the energy storage device will absorb some energy from the power source and store the energy in the energy storage device. When the actual power of the server system is higher than the power budget, then the energy storage device will discharge the stored energy to provide extra power for the server. This process goes on until at this time the energy storage device is fully charged, so it couldn't absorb more energy. In the last period, the energy storage device discharged to provide extra power. In such a system, we can see we don't do any management on the server side, but we still manage to control the power consumption of the entire system. I mean, the energy storage device and the server, this system, the power consumption never go higher than certain value. This is exactly the problem we are trying to discuss in our SuperCap paper. Along this direction, there has been very nice work, but they all assume using traditional batteries. However, in this particular application scenarios, there are several limitations for using batteries. For example, usually a battery has a very limited number of charge and recharge cycles. But in energy storage device for power control, we need to frequently charge and discharge the energy storage device. So maybe the battery is not the best choice we have here. Another insufficiency for battery is the long recharge time. We all use batteries in our cell phones, so we know it takes time for the battery to recharge. In order to address those inefficiencies, we evaluate the possibility to use a supercapacitor as a replacement for traditional battery as energy storage device in power control. Supercapacitor is basically a capacitor, but it has a very large capacity. It has much more charge and discharge cycles. It also has very short recharge time, which are very preferable for this application scenario. The target of our project is to reduce the operation cost of a data center. This slide shows our design and the high-level introduction for the power infrastructure in the data center. Let's start from the left side. We can see the power grid will provide the power for the entire data center. The power grid power first goes to UPS, uninterruptible power supply. After UPS, the power will go to PDU, power distribution unit. The PDU will distribute the incoming power to each rack. Rack is basically a big box. We can install all the servers in the racks. In the PDU, there is a very important component called the circuit breaker, CB. Each CB is associated with one rack. When the total power consumption of one rack is too high, higher than the threshold value for the circuit breaker, then the circuit breaker will trip up to protect the other power infrastructure. So circuit breaker trip up is a very bad scenario in data center operation. We want to avoid that. Inside each server, we have a power supply unit, PSU. It will convert the AC power to DC power and provide DC power to the onboard components. The processor is one of the most power hungry one in the usually in a server. Our design includes two parts, the supercapacitor and the power control unit. The supercapacitor is basically a hardware unit. It will charge and discharge the energy. The power control unit will control the charge and discharge status of the supercapacitor and control the frequency level of the processor in order to coordinate those two components to ensure that the power consumption of the server never go higher than a certain value in order to enforce of our power budget. This is the picture of the proof of concept prototype of our supercapacitor. More details about the circuit design could be found in the technical report. The key design part in this project is the power control unit. Since in this project we have two adjustable components, the frequency of the processor and the energy storage device. How to coordinate those two components is very important to enforce power budget. We have discussed different policies. Here we take performance priority, the perf first policy as one example to explain how we coordinate the frequency of the processor and the energy storage device. Let's say If the power consumption of the system is currently lower than the power budget, then we have two options. We can either increase the frequency of the processor to increase the power usage, or we can recharge the energy storage device to reserve the energy for later use. Since in this perf first scenario, we want to give high priority to performance, so we first increase the frequency of the processor to improve performance until the frequency reaches the highest available level. Only by then, we started recharging the energy storage device. In another case, when the power consumption is higher than the power budget, since we give high priority to the performance, so we first discharge the energy storage device until the energy storage device is totally drained out. Until then, we started to lower the frequency. So by using this policy, we coordinate the frequency of the processor and the charge-discharge status of the energy storage device to make them work together to ensure that the power consumption of the system never go higher than the power budget. So far, we've seen that by using a power control unit, we can control the power consumption of each server. But how power control can save the operation cost in the data center? Here we offer one example. We've learned that a circuit breaker is associated with one rack. If the total power consumption of the rack is too high, the circuit breaker will trip up. That means when we host a lot of servers in the rack, there is a possibility that all the servers they spike in terms of power consumption at the same time. So the circuit breaker will trip up. In order to ensure the safeness of the hosting, we cannot deploy a lot of servers in the rack. However, within the same power infrastructure, if we can control the power consumption of one server never go higher than certain value, that means we can safely host more servers in one rack. Because in the data center setting, a lot of overhead money, a big chunk of money goes to the construction of the data center, or the cooling facility, or the power infrastructure. Those money has been spent. The more servers we can host in the data center, the less money for each server, the less overhead for each server. So power control can reduce the operation cost of a data center by enabling more servers to be deployed in the existing infrastructure. That's how power control can reduce the operation cost of a data center. We evaluate our system in a self-developed simulator. We evaluate the total cost of the ownership, including the building cost of the facility and the cooling and the power infrastructure. We evaluate different construction options, including the supercapacitor-only case, and the battery-only case, and the supercapacitor plus battery case. In our evaluation, we find out that using supercapacitor only will give us the most total cost saving in our studied cases. Here we recap the whole talk. The root problem we are trying to solve here is to optimize the computer system performance and assign the power budget. We studied the problem on the component level, chip level, server level, and the system level. We use different characteristics on those different levels to leverage those special characteristics to optimize the performance of the system. Looking forward, there are several problems that I want to explore. The first one is the green computing. Suppose we have a solar panel. We use a solar panel to power up a data center. On the power generation side, how much power the solar panel can generate depends on the solar radiation condition. in the server room, how much power is using here is decided by the workload condition. The problem here is the workload condition is independent from the solar radiation availability. So there is a mismatch here. There is a possibility that when we want to use a lot of power in the server room, the solar panel cannot generate that much power. So we need to manage the power consumption of the server room. We can either use energy storage device, for example, the battery or supercapacitor. We also can use a frequency scaling on the servers in the server room. But the high-level idea is to manage the power consumption of the server room to match the generation side profile. That would be a very interesting problem to me. Another problem I want to explore is the energy-related cost minimization. Traditionally, when we do energy-related cost minimization, we usually assume that the less energy we use, the less money we spend. But in the current smart grid power electricity market, the electricity price is changing all the time. In North America, it's 5 minutes. Every 5 minutes, the utility company will charge the power, especially the industry power user, a different electricity price. So there is a very strong incentive for us to use more energy when the electricity price is low and use less energy when the electricity price is high to fully leverage the price difference at a different time. That will make the whole cost minimization a very interesting optimization problem. The last problem I want to introduce here is the heterogeneous platform. In the near future, maybe everybody here has a cell phone or a tablet. And in our classroom or at home, we may have a desktop or laptop computers. On the remote side, we have a data center to support cloud computing. How to coordinate all those components to make them work together to minimize the overall power consumption, as well as to optimize the system performance, is a very complex and interesting problem to me. Thank you so much for attending this talk. Really appreciate your time.